Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc over in the University of Helsinki and the Helsinki Institute of Physics in Helsinki, Finland. And I'm a cosmologist. So that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a physicist, I love being a cosmologist, and I love chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about physics, about cosmology, about space, about academia, about life in Finland. You can ask me anything you want, and I will do my best to try to answer your questions. If you haven't done so yet, please do like this video, subscribe, leave a comment, do all of the usual YouTube stuff. It really does help boost engagement. And if you're over on Twitch, there's buttons you can press on Twitch as well. That also helps boost engagement. And then I get to chat to more people about the amazing things I get to work on. I see we have a bunch of regulars coming in. Prath, Mita, Paul, great to see you. Thank you for coming back as always. And to any first-time viewers, welcome. It is great to have you here. Hey, Ben, great to see you as well. So today's going to be a fun stream. There is a lot to talk about today. I actually have a topic planned, and this is not just going to be a random thoughts with Diana afternoon like it often is. There's actually a topic today, and I'm very excited about today's stream. But first, let me just say thank you to everyone for coming back. I know Cup of Cosmology has been offline for 4 weeks consecutive now. It's been quite a gap. It's been a combination of reasons, it's mainly been me doing a lot of things. And these things either fell on a Sunday or Sunday happened to be the only day of the week where I could actually have a break. And as some of you know, I do need to moderate my energy levels. So I think I've missed 4 streams consecutive. 2 of them are because I had events on Sunday, and 2 of them are because I had events on Saturday and was a bit too tired on Sunday to do a live stream. But now we're back, which means we have a month worth of results to talk about. So it's a lot to do, a lot to say, a lot to talk about today. As always, even though we have a topic planned, we're going to be staying more or less on track as I can, which, as you know, is not really on track because we will be jumping around a bit. But even though I have a topic, please do ask any and all of your questions. If they are on topic, I will try to answer them. If they're not, I'll try to incorporate them whenever I can. But as always, please feel free to ask any and all questions you have. The questions is what makes Cup of Cosmology fun and interactive and helps include you all. So please do ask me any questions at any point during the stream. As always, I know some of you will. Okay, so exciting stuff today. My cats are very active. Should add the disclaimer that neither me nor my cats have had dinner, which means I will not be on as late as usually, potentially. However, do you not have subscriptions enabled on Twitch? I should. To my knowledge, I do. I believe. However, to be honest, I have very little idea on how Twitch works. I set it up at some point. I know Restream sends it out to Twitch, and I do very little effort in actually getting Twitch up and running. I might actually just close the Twitch side of things soon and switch entirely to being a purely YouTube-based program. We shall see. But there's a chance that the Twitch stream is going to gradually be phased out coming soon. But we shall see. I'm not completely sure on if it's worth keeping the Twitch stream, but that's a problem for the future. But one good thing about the fact that I have not been online for the last 4 weeks means we missed that terrible period where the time zones don't align, because in the US, you all switched to daylight saving time 3 weeks ago. We switched to daylight saving time last night, which also means that today I have no idea what time of the day it is, which is why I haven't had dinner yet and why my cats haven't had dinner yet. But it also means we missed the 3 weeks where people miss my stream or come in late or come in early because of the time zone shift. So we're all back on the time zones that we should be on, which is always good. And as usual, you all know I hate daylight saving time and think we should abolish it. So mandatory rant insert here. But you all know that already. We do not need to do that again. Oh, it is apparently Zoomies time. My cat just sprang out of the bedroom. High on Zoomies. So there might be some distractions happening around the house because cats have Zoomies. Okay, so there are 4 things that we have to talk about today. But before I can get to them, I need to give you the context for them. So Yes, feel free to subscribe on Twitch while it is still there. There's just a small chance that at some point in the next month or so, the Twitch stream might disappear. But for now it's there. I do always get 2 people watching on Twitch consistently every week, every time there's a stream. So for those 2 people, maybe I keep the Twitch stream alive. We shall see. I'm pretty sure one of you is actually on both YouTube and Twitch to boost viewers, and I appreciate that. Thank you. Okay, so there was a very exciting week for cosmology in March. There were a bunch of missions that released data or new results all within the span of a few days of each other. Some I knew were going to happen, some I did not know were going to release data. So there are 4 things or 4 experiments that have released data, and we're going to talk about all of them. The first one on the 18th of March was the Atacama Cosmology Telescope released its DR6, data release 6. This is extremely cool result. It's CMB, cosmic microwave background radiation. Don't worry if you don't know what any of these words are yet. We will get into that. So we have new results from the Atacama Cosmology Telescope. Also on the 18th of March, we got the next result from DESI. DESI is a dark energy spectroscopic instrument. As many of you already remember, about a year ago, April last year, there was a big release from the dark energy spectroscopic instrument that showed some information about dark energy that was surprising and unexpected. That was based on 1 year of data. On the 18th of March, they just casually released the next data release based on 3 years of data. So obviously, we have to talk about DESI results. On the 19th of March, 1 day later, we got the very much planned and advertised and announced Q1 release from Euclid. So the Q1 release is the quick release 1. And the quick release 1 is the first major release from Euclid that contains a bunch of cool information, a bunch of cool photos, but does not yet contain cosmology results. Let's be very clear about this already from the start. The Euclid results that I'm going to discuss are amazing. It's not yet cosmology results. I'm not going to be solving dark energy and dark matter today in the stream, although caveat on that, because DESI has something to say about that. And then on the 25th of March, the KIDS survey, the Kilo Degree survey, released their legacy final database. So KIDS is a telescope that is looking at galaxy shearing, so how galaxies are distorted, and using this to reconstruct the matter in the universe. And there was the final KIDS legacy release after KIDS 1000 a few years ago. Now we had KIDS legacy. And their results are also extremely interesting and very significant for cosmology. So we had 18th of March, 18th of March, we had DESI and Atacama Cosmology Telescope. I'm going to mispronounce it every single time because the acronym is ACT. So my brain reads it as Akatama, but it is the Atacama Cosmology Telescope. Anyway, 18th of March, we had ACT, the Atacama Cosmology Telescope, and DESI. 19th of March, we had Euclid, and 25th of March, we had KIDS. What a week! It was a very intense week. I knew that the Euclid results were coming. I suspected DESI was going to come out around this time, but I didn't know the exact dates. I had no idea about ACT and KIDS release. So this was very fun because I was just checking every day and it was like, oh, new results. And because there's been a gap in the Cup of Cosmology streams, now we get to cover all 4 data releases in one stream. So it's going to be a ride. It's going to be a fun ride today. There is a lot to discuss because we got 4 new cosmology experiments or 4 cosmology experiments releasing data. Some are first releases, some are final releases, and all of them are very interesting. So let's jump into this. But before we jump into the results, I'm going to give you some background so you understand what I'm talking about. Okay, and let me just catch up with comments. I realized I am speaking quicker than usual. Deep breath. Whew. So, deep breath. Yes, I have a tendency to get carried away and talk very quickly, and then I need to be like, okay, let's calm down. Not everyone speaks as quickly as I do. I can chill. Hi, Scott. Great to see you. You are not late. Don't worry. You just missed the introduction. But the main thing is there are 4 new cosmology results and data releases to discuss. and we're going to jump in. But before we jump into that, I want to give you some background information. Question from John here: is there a new CMB image to use? That is potentially something you will see very soon. The short answer is yes. It does not replace the blank CMB sky, but we do have a new CMB map. The a cappella telescope, it sings its results. I love that, Paul. As someone who somehow loves a cappella, I appreciate that joke. I'm not going to go on a music tangent here. A cappella is cool. Anyway, let's talk about the standard model of cosmology. What is our universe made of, and how do we know these things? Key questions. So first up, the universe, as far as we know, has three main components. Everything we see, everything we're accustomed to, everything from me to my very excited cats to my tea mug, all of this is normal matter. Normal matter only accounts for about 5% of the energy budget of the observable universe. Then there is 26% in the form of dark matter. Dark matter is this weird type of matter that interacts via the gravitational force, but doesn't interact via the electromagnetic force. This means that dark matter is essentially invisible. It does not emit light, it does not transmit light, it does not receive light, it does not interact with light in any meaningful way. However, dark matter does interact gravitationally, which means it can distort space-time, and light traveling through space will feel this curvature space-time caused by dark matter. So dark matter doesn't do much. It's kind of invisible, but it does interact gravitationally, and it is the glue that holds our galaxies together. It provides a scaffolding for the rest of the universe to be built upon. And then we have 69% in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe. We know that the universe is expanding. We know that the universe is expanding faster today than it has in the past. And we believe this is caused by dark energy. So dark energy is the 69% of the energy budget of the observable universe. We know that dark energy is driving the accelerated expansion of the universe. We don't know much else about dark energy. For the matter of simplicity, we often refer to dark energy as being a cosmological constant, something that behaves the same throughout history of the universe, just being more or less present as the universe expands and as dark energy dissipates away differently to other components. So in our general idea, dark energy is a cosmological constant. It's a constant energy that is pushing the universe outwards, and that's pretty much everything we know about dark energy, or so we thought. So these are the three main building blocks of the universe. And as Paul is saying, it is funny to call the smallest slice the normal type, because there's only 5% of normal matter, but it is the one we're used to. We cannot see dark matter, we cannot see dark energy, but we can see normal matter, which is why it's called the normal matter. Also, scientifically, we normally call it baryonic matter, which just means it can cluster together and interact with light. But calling it normal matter is a more standard nomenclature, the standard name for it. Okay, so this is our standard model of cosmology. Our standard model of cosmology is known as lambda CDM. Lambda stands for cosmological constant, CDM stands for cold dark matter. What we mean by cold here is that the dark matter doesn't interact with anything else. It has a very slow speed as it's moving throughout the universe, but it does have mass. So we have the main components being lambda and CDM. Dark energy as a constant and cold dark matter. So the question is, where does our standard model of cosmology come from? And the answer to that, obviously, as you regulars know, is the cosmic microwave background radiation. This is a snapshot of what the universe looked like 380,000 years after the end of inflation, which means about 13.2 billion years ago from our perspective. And what we can see here is the background glow that's everywhere in the universe. So, about 380,000 years after the end of inflation, the universe has three main components. Well, you have dark matter that's doing its thing, it's not interacting with anything, but then you have three main things. We have protons, we have electrons, and we have photons, which are particles of light. In the early universe, everything is very hot and very energetic. The protons, the electrons, and the photons, the particles of light, are constantly bumping into each other. As the universe gradually cools down, the protons and the electrons can combine together to form the first neutral hydrogen in the universe, or the first atoms in the universe. And at this point, the photons, the particles of light, break away. They break away and they start traveling freely throughout the universe. Those photons have been traveling freely ever since. By the time they reach us today, their wavelength has shifted, so every particle in the universe has an associated wavelength. It's time to bring out the slinky. Every particle in the universe has a wavelength. As these particles travel throughout the universe, this gradually expands. This means that light can shift from being in one energy range to being in another. So the photons that make up this background here are now in the microwave range of the electromagnetic spectrum. They are everywhere we see, in every direction we look in the universe, behind everything else, we find these photons. And this is why it's called the cosmic microwave background radiation. Cosmic, because, it's in the sky. Microwave, because it's in the microwave range of the electromagnetic spectrum. And background radiation, because it's everywhere behind us in the universe. This is the CMB. Now, the different colors here, the different temperatures, show us the energy of these photons. So the bluer ones were slightly colder, the redder ones were slightly hotter. And based on this energy or the temperature of these CMB photons, we can understand the statistical properties of the early universe. So by looking at this map, we can see what the universe looked like in 380,000 years after the end of inflation. So really what we take away from here is the overall statistics. How many orange spots are there? How many blue spots are there? How are the orange and blue spots distributed in this map? So this is a map of the whole sky, as if we're looking around us. We are in the center of this map. Okay. Cosmic microwave background radiation, oldest light in the universe, snapshot of the baby universe. By studying the CMB, we can figure out what standard model of cosmology best describes this image. So what we do is we run a computer simulation where we try 1 billion different realizations of the universe with 1 billion different cosmological models, and we see which one fits the data the best. And from the CMB, we get the values for our standard model of cosmology. Hey, just Takina here. Great to see you as always. And John, I see you have two very, very cool questions. I will get to those. Do not worry, I will get to those questions. So, from the CMB, we get mainly 6 numbers. 6 numbers that are needed to describe lambda CDM, so our standard model of cosmology. These are 2 numbers telling us how clumpy the initial universe was after the end of inflation. So one of us tells us how many clumps, and the other tells us how big these clumps are relative to each other. Then the remaining 4 numbers, one of them is time at which stars turned on, and the remaining 3 are going to be the amount of dark matter, the amount of dark energy, and the amount of normal matter, the amount of dark matter, and the age of the universe. Obviously, once we've fixed how much of the universe, well, once you have the age of the universe and 2 of the density, so the amount of matter and the amount of dark matter, from there you can calculate the amount of dark energy. So from this CMB map, we get the values that I was showing you before: 4.9% normal matter, 26.2% dark matter, 68.9% dark energy. So our standard model of cosmology is just represented by these 6 numbers. And then from the CMB and using our standard model of cosmology, we can calculate additional things. For an example, how fast is the universe expanding today? This is known as the Hubble constant. We can also calculate how clumpy the universe should be today. For an example, how much matter there should be if I focus on a specific scale. This is known as sigma 8 or S8. So these are values that we get from the CMB using our standard model of cosmology. But the CMB gives us the 6 values of the standard model of cosmology. So this is very cool. Then we have a bunch of other observations that we can use to kind of test our standard model of cosmology. These include things like how much matter clumps across the universe, how galaxies look, how galaxies behave, how dark energy appears to behave. And we take all of these things together, and we have not found any model that fits all of the data better than lambda CDM, our standard model of cosmology. However, there have been some small problems with lambda CDM or with our standard model of cosmology coming about from when we compare the results we get from the CMB with other experiments. We have found a few small inconsistencies. And I just want to emphasize here that the map that you see here, this CMB map, was taken by Planck. Planck was a mission from the European Space Agency that launched in 2009 took data for 5 years, and we have all of the data. This is the final map from Planck. This is considered the most precise map of the CMB ever. So this here is the most precise map we have of the CMB, taken by the Planck mission, which was a joint project of the European Space Agency and NASA. So, just pressed the wrong button, and now my whole screen has gone weird. Okay, let me just fix my screen a minute, because I don't know what happened there. I'm pretty sure you all can't see that, but my screen just kind of went weird because I pressed the wrong button. That was the button. That's the button I wanted to press. Okay, all good. Back to normal. Just me being confused by technology. Okay, so there have been a couple of inconsistencies that have appeared over the last few years, and they're not enough to say our standard model of cosmology are wrong, but they have been enough to raise some questions as to kind of like what is going on here. Now, the most well-known of these problems are ones that I've talked about a lot in other streams, but the first one, and the most notorious one, is what is known as the Hubble tension. So I mentioned before that once we have the CMB and our standard model of cosmology, we can calculate the expansion rate of the universe today. And if you do this, you take the CMB, you project it forward, because of course this is a map of what the universe looked like 13 billion years ago. So then you project it forward to today, and then you can ask the question of, if I'm projecting this forward to today, how fast is the universe expanding today, assuming our cosmological model? And if you do this, you get a value of 67.5 in some units that you don't really need to worry about, 67.5 plus minus 0.5. There's another way you can measure the expansion rate of the universe today, which is by using local measurements. So you can use supernova, which are stars that have a specific amount of brightness. So a supernova is a star that's reached the end of its lifetime, and it collapses and explodes in a supernova, massive explosion. And we can use these explosions in nearby galaxies to measure distances, and then we can use different stars to calibrate these supernova, and we can get an idea of how fast the universe is expanding today. And if we get these measurements today, we get a value of the expansion rate of the universe of 73.4 plus minus 1.2, which is still very close. You know, we got a value of 67 and 73. We could have got values of 67 and 500. We got values of 67 and 73. This means that the measurements are close, but they are not close enough. They were what we call a 5 sigma tension between them. So sigma, when we talk about sigmas in cosmology or in science in general, sigma means our degree of belief in something. When we say something is at 1, 2, 3 sigma, it's mildly interesting, but could still be a statistical fluke. Anything above 5 sigma is considered a discovery in cosmology. Now, when we talk about data sets being in tension with each other, we use sigma to quantify how far apart these data sets are. So if we say they're within 1 sigma, they're very close. You might have one value here and one value here. Like if one mission had given us 67 and the other had given us 68, we would say, okay, they're quite close together. 2 sigma means they're starting to shift apart. 3 sigma, 4 sigma, 5 sigma. It tells you how far apart they are. When we say that there's a 5 sigma tension between CMB measurements and supernova measurements for the expansion rate of the universe, we're saying there's like a 1 in a billion chance that this is a random statistical accident. There's something that we need to explain. So the Hubble tension has been one problem we found with lambda CDM, our standard model of cosmology. Another problem we found with our standard model of cosmology is what is called the sigma 8 tension. Sigma 8 or S8, I'm just going to call it S8. S8 is a measurement of how much galaxy there is on a specific scale of 8 megaparsecs. You know, if you've ever heard that Han Solo did the Han Solo did the race in 12 parsecs. That makes no sense. Parsec is a unit of distance, not a unit of time. 1 megaparsec is the average distance between galaxies. Minor detail there, just for Star Wars reference. So sigma 8 S8 is a parameter, is a number that tells us basically how matter clumps together when you take a box of about 8 by 8 galaxies. If you take that box, how is matter going to clump together? And this is a number that you can get, again, from the CMB, from the cosmic microwave background radiation. It's not something we measure here. It's something that we can get from here projected onto today using our standard model of cosmology. We can also get a value of S8 from lensing experiments that are doing shears. So shears is when you get a galaxy. This galaxy can be distorted due to gravitational lensing. Gravitational lensing is when you have a big massive object like a big clump of dark matter. This is going to distort space-time. So the light coming from a distant galaxy is going to feel this distortion of space-time and is going to give us a distorted image of the initial galaxy. So by looking at how distorted these galaxy images are, we can understand the matter that is between us and these distant galaxies. And if we do this and looked at how sheared or how distorted these galaxies are, we do what is known as a cosmic shear experiment, and we get a different value of sigma 8, of S8. Yes, in Star Wars, the Kessel Run is explained as like he completed the race in record time, and the time is like in 12 parsecs, and it doesn't make any sense. I think then they kind of retconned it to be that he took a shortcut, so he completed the race in a shorter distance, but yes, it doesn't make sense. Not that Star Wars is known for being scientifically accurate in any other aspect either. You know, the moment you throw in midichlorians, well, they lost any scientific credibility at the Force, but then the midichlorians lost it for me. I am not a fan of the prequels. Anyway, back on topic. Back on topic. Yes. So we can use cosmic shear experiments to get a measurement of S8. Now, when we compare the values of S8 we get from CMB and from cosmic shear experiments, there was a 3 sigma discrepancy. These were 3 sigma apart from each other, which again is not catastrophic. It's not as bad as the Hubble tension, as the expansion rate of the universe tension, but still 3 sigma is not nothing. It starts to be very interesting. And one of the main drivers of this tension, or one of the experiments that has found this discrepancy with S8, is the KIDS experiment, the kilodegree survey, which is a ground-based survey taking data, looking at a lot of galaxies, and trying to measure how distorted these galaxies are. So in 2000 and something, 2020, I believe, I wrote down the wrong number here. Yes, in 2020, it has to be 2020 here. In 2020, we had the KIDS 1000 release, where they found this 3 sigma tension to the Planck measurement. So the CMB value that we measured from Planck and the KIDS value for the sigma 8, for S8 were 3 sigma away with each other, away from each other. So this was one of the tensions that we had in cosmology. Okay, just going to answer questions, and then I want to mention another problem, issue, interesting thing we've had in cosmology over the last few years, and then I'll get into the new results. Comment here from Takina: I don't see how local measurements correlate to origin measurements of the universe. I'm referring to Hubble tension. Because of time dilation that happens due to the nature of space-time, so wouldn't disrupt measurements. So these are things that we can take into account. Right, we can look around the universe today and we can ask the question of how is the universe expanding today in my local neighborhood? And for this, you just need measurements of 2 things. You need to figure out how far away galaxies are and how fast galaxies are moving away from you. And if you do this, you can build what is known as a Hubble diagram. And from the Hubble diagram, you can read off the expansion of the universe today. Now, when we use the early universe measurements of the CMB, and then we study our standard model of cosmology, we get our standard model of cosmology from the CMB, and then we can project it forward. We can basically run a simulation and say, okay, now play on 13 billion years of cosmic evolution, spit out what the universe looks like today, if that is what it looked like at the time of the CMB. And you can do this, and then you pull out the expansion rate of the universe today by kind of projecting the CMB forward to today. And here we do need to take into account things like the universe is expanding. This is taken into consideration. We need to take into account things like we might now be in a local void or a local group that has more or less density to the measurements we're doing. So these are all things that are taken into account. And this is why when we project the CMB forward, we need to assume a cosmological model. So we don't directly read off the expansion rate of the universe from the CMB map. We calculate it by projecting that forward to today. And when we do this projection forward is where we assume a standard model of cosmology. So this is the same for S8. It's not something we're reading off directly from the CMB, it's something we are projecting forward from the CMB and getting the value. So both of these forward projections from the CMB to today assume a cosmological model. So this is why the Hubble tension and the S8 tension have been phrased often as problems with lambda CDM. They could also be problems with some of the measurements. But because we use our standard model of cosmology to get these numbers out of the CMB, maybe if we're getting the wrong numbers, it's because we're using the wrong model. So the the S8 tension and the Hubble tension, the expansion rate of the universe tension, have been considered to be problems with our standard model of cosmology. So yes, these are often considered the biggest points of contention of our standard model of cosmology, the things that are not completely as well understood as we would like. There are many different explanations for them. None of them are very convincing. No one has been able to successfully find an explanation for why we're getting different values of the Hubble constant and of sigma 8. Then there's been another interesting thing. So this map here, again, this map that I'm going to show you here is from Planck. Planck measured the temperature of these photons, hot and cold, orange, blue with sliding scale. This map that I keep showing from Planck was released in 2018. It is the most precise map we have of the CMB. It's one of the only all-sky surveys of the CMB. Then we have the Atacama Cosmology Telescope. The Atacama Cosmology Telescope is a ground-based telescope, so Planck was a space one. Atacama Cosmology Telescope is a ground-based CMB mission that stares very intently at one region of the sky. So while Planck could do a full sky survey, Atacama can stare very intensely at one region of the sky. So we get less overall amount of information, but we get very, very precise information about that patch that we are staring at very intently. Atacama Cosmology Telescope, apart from measuring temperature, was also measuring the polarization of the CMB. So apart from temperature, these photons, these particles of light that make up the cosmic microwave background radiation, are vibrating in a specific way. So even if light is traveling towards you, it can have a vibration in a different direction. It can either be traveling kind of like that, or And this is something you might be used to if you have any type of sunglasses or a polarized filter, where you can do the cool thing where if you turn your head, things become more or less clear or change colors. Or if you use your polarized glasses, you can see the bottom of a lake if you're staring at it. This is all related to looking at light that travels with a specific vibration or a specific direction that it's moving in. So, Atacama Cosmology Telescope is measuring the temperature and the polarization. Now, there's one very interesting thing about the Atacama Cosmology Telescope. In 2021, we had DR4, data release 4 of the Atacama Cosmology Telescope, and this was measuring the standard model of cosmology and seeing if it's something that agrees with the measurements we got from Planck. Because, again, if we're using this map to project forward to today and get our standard model of cosmology, we need to ask the questions of what goes wrong to give us different values of a Hubble tension or of Hubble constant and of S8. So if it's not the standard model, either there's a problem with our model or there's a problem with one of the measurements. So the Atacama Cosmology Telescope was kind of a cross-check of what Planck was doing and was also supposed to go further. Now, the data that was released in 2021 by the Atacama Cosmology Telescope did not completely agree with Planck. There was about 2.5 sigma difference in the values of our standard cosmology parameters. So the amount of dark matter was slightly different. The amount of dark energy was slightly different, not dramatically different, but slightly different. The age at which the first stars turned on was slightly different. Not dramatically different, but slightly different. So then, depending on what you wanted to do with this data, this was either phrased as being 2.5 sigma agreement with Planck or 2.5 sigma tension with Planck, because then that tension gives people room to play about with different models. So there have been a bunch of cosmological models over the last few years that have used the Atacama Cosmology Telescope to kind of shift things away from lambda CDM, because the Atacama Cosmology Telescope was slightly away from the lambda CDM values that we got from Planck. So, just to recap quickly, we have our standard model of cosmology, dark matter, dark energy as a constant, 5% no more matter, a universe that is kind of well understood, but there were some issues with the values of lambda CDM and the projections of lambda CDM to today. When we take the CMB data and we project forward to today using the standard model of cosmology, we get problems with sigma 8 or S8, the amount of matter on specific scales. We get problems with the expansion rate of the universe. And when we compare the default de facto best cosmology mission, CMB mission we have, which is Planck, with a newer one, which is the Atacama Cosmology Telescope, we were getting a 2.5 sigma discrepancy. Okay, welcome to March 2025. Let's revisit everything I just said. It's been an intense 10-11 days for cosmologists. Okay, some questions here. Comment from Takina from when we're talking about projecting these things forward. So it's not a standalone measurement, but a measurement to be acknowledged or exists within a system of other measurement alongside model of the universe. Exactly. Yes, exactly. We don't measure the expansion of the universe from the CMB. We measure our standard model of cosmology and we use that to project forward and get the Hubble constant today. Yes, depending on what type of polarized sunglasses you have, if you're at a shallow lake or a shallow water body and it's not overly dirty, you can actually see the bottom, depending on, because the water is going to polarize the light slightly, or the light reflected off of the ocean is going to be slightly polarized. And if you have good polarized glasses, you can kind of see, you get more depth perception in the water if you have polarized sunglasses. It's very, very cool. It's something that you can try. If you have polarized sunglasses, go stare at a lake. You know, it's always good to go stare at water. Go stare at a lake or a shallow sea or something. If you have polarized glasses, obviously if it's several hundred meters deep, you're not going to see it. But if it's like something you could stand in, you might be able to see the bottom, assuming it's clean water. Okay, 38 minutes or 40 minutes after making my tea, it is at perfect drinking temperature. I am a wuss with hot drinks. I need my drinks to be very cold before I can drink them. Yeah, comment from Prathia, just kind of agreeing with what I was saying, that light reflected from a water surface is polarized, so you can see deeper if you can cancel out the polarization with glasses. Exactly. Comment from John, I've heard the term birefringence used in discussions of CMB polarization. Can you explain what this is and its significance? I should be able to, but I'm not going to explain this today. It's not something that... It's a very cool effect that you get with light, where you get kind of a double reflection, and you get cool physics coming out with that. And it's something that we do look for in the CMB as well. But it's not something I feel comfortable discussing without rereading a paper first. And it's not part of the main results I want to discuss today. Okay, so 40 minutes into the stream, I've just given you general background, state of the universe, standard model of cosmology. What are we doing now? Okay, 18th of March, we get data release 6 from the Atacama Cosmology Telescope. In this, we get a very, very, very cool new image, which I'm going to bring up now. I have not had time to put these in my slides, so I am going to screen share. So this may or may not be a bit buggy. Let's see. For now, it seems to be working okay. Great. What you can see here is the final map. So DR6 from the Atacama Cosmology Telescope is probably the final release. I believe they have finished taking data. Other than reprocessing the data, this is the final release. So what you can see here is a new version of the CMB map to be compared to... Can I put multiple things on the screen at the same time? I probably can if I do this. Haha, there we go. Okay, the thing you can see over there, or up there for me, I hope it's not flipped. The thing you can see, the big thing, that's our standard Planck map. The one you can see up above me, that is the new map from the Atacama Cosmology Telescope. Ignore the lines you can see on it for now, just focus on the orange and the blue. You can see it's a smaller chunk of the sky. It's not taking the full picture. It's a smaller chunk of the sky, but it is staring very intensely at this small chunk of the sky. So on this small chunk of the sky, you get a bit more precision. Okay, let me get rid of the standard one and just leave us with the new one. Oh, actually, I'll put myself side by side with it here. Okay, so this is what we have from the Atacama Cosmology Telescope. Let me zoom in a bit because this is really amazing detail here. And let's just zoom in, zoom in, zoom in, zoom in. So the numbers that you can see at the top and on the left here, this just indicates, oh, you can see my cursor, cool. This just shows you the kind of degrees on the sky that we're looking at. These are just coordinates. So you have the kind of galactic coordinates of which part of the galaxy we're looking at. And you can see we have the orange, we have the blue spot, same as we had before. On top of this, they've added these lines. These lines are the polarization of the CMB. So we do not measure these lines directly, but this tells us which direction the CMB photons are vibrating in. You can see that there are kind of patterns. Here you get this swirl, here you get this swirl, here you get things moving away from each other. So the general way to read this is if something is a circle, it's pulling gas. Something is a circle, the gas is moving outwards, or the CMB photons are moving outwards, kind of vibrational. And if it's something that has lines moving away from it, gravity is the driving force. So this kind of highlights the battle between gravity and pressure in the CMB. And the lines are superimposed on top. And one cool thing that you can see here is how you get more of the swirls in the blue area, which is what we expect, and you get more of the photons moving away from each other, vibrating in different directions in the more hot spots, which are the different gaseous regions. And you can see there's incredible precision on this map. So that there is the new map from the Atacama Cosmology Telescope. Coming from Takina here, how does it actually look like? Like, what is actually the reality of things if we're standing very close to it? Well, I guess it's radiation. Yeah, it's radiation. We will not be able to see this just with our eyes because this is in the microwave range of the electromagnetic spectrum, and that's not something our eyes are sensitive to. So this is why we need detectors to measure this. And obviously, if you try to do this measurement in the kitchen, you have a lot of other microwave waves going around. So it's not something we can see directly. It's something that we have to kind of go to space to measure. So there's the question from Paul here, which I was hoping nobody would ask, but it's a logical question to ask. Why does the polarization imply which way the plasma is moving? You did not mishear me. That is indeed correct. And this is related to when the CMB photons are produced, as the universe is cooling down, the protons and the electrons combine together, the photons break away. The way they break away is going to be influenced by the density of the plasma, of this early universe plasma, where we have all of these photons, protons, electrons. So what is happening in that plasma is going to influence how the CMB photons vibrate. Now, specifically how the interplay between polarization and the direction the plasma is traveling, I did not have time to refresh my memory of, but there was a cool graphic from the Atacama Cosmology Telescope people that just had this as a reference, like, if the lines go like this, the plasma's doing that. If the lines go like this, the plasma's doing this. It was like, that's a very cool thing to share with people. But I did not then do the work of figuring out why. So it is related to how the CMB photons are produced and the densities of the plasma at the time the CMB photons are produced. But that's as in-depth as I can give that answer for now. Excellent question, Paul, as always. It's just a question I was like, I hope nobody asked me follow-ups on that. So of course you're going to ask me a follow-up on that because it is a logical thing to ask. It's a very good question. Okay, so the big question is, apart from this amazing map, we have a new CMB map. I know, John, you asked me that earlier. Do we get a new CMB map? Yes, we do. We have this one. This is our new CMB map. It's not as all sky encompassing as Planck, but it's still very pretty. And I love the polarization imposed on top. It's just a very, very pretty map. But the big question is, what did they find from this? So as a reminder, in 2021, data release 4, the Atacama Cosmology Telescope was 2.5 sigma away, or in an agreement with, depending on your perspective, from Planck. Data release 6, this map that I've just shown you, agrees to within less than 1 sigma deviation with the Planck results. Almost perfect agreement with Planck. So this is cool. This is very cool because for the last 4 years, people have been wondering, why does our new CMB mission give us slightly different information to what is considered the state of the art for CMB missions? What's happening here? And it turns out there was something in their analysis that they found that could be improved, a way of analyzing the data that wasn't as precise as it could be. And by taking this into account, they now shift back towards the Planck values. So this is something that is well understood within the Atacama Cosmology Telescope. They're not now scratching their heads like, why did things move? Why did it move away? They know why it moved away. They've understood what was happening in their analysis, and by improving their analysis in DR6, they recover the Planck values. So this, if you're a Planck person, if you're somebody who thinks this map here is the answer, this map here is the CMB, this is good, this is our state of the art, if you believe that, this is amazing news, because the Atacama Cosmology Telescope is now refining what Planck has found. After the last 4 years of us wondering, why is it 2.5 sigma away? It's not dramatically away, but why is it shifting a bit? Turns out it's not. So if you like lambda CDM, if you like our standard model of cosmology, if you like Planck, this is great news. If you like these other models that you could play about with the Atacama data, the previous Atacama data, if you like those models, that is not good news. But this is something that is very cool, and it's also kind of a sign of why science is an ongoing process. You know, we got the Atacama Cosmology results a few years ago, and since then they've revisited every step of their analysis, they've revisited everything, they've got more data, they've reanalyzed everything, and now they get a slightly different result, but they understand where this different result is coming from. And now from a CMB perspective, all our CMB missions are telling us the same information. So that is very, very cool. If you're a CMB fan, that is very cool. If you're a fan of the standard model of cosmology, this is very cool. So this was released on the 18th of March. I actually saw it a few days later, and I was surprised by this. There was a small press release that went with it, but yeah, it's very, very cool that, you know, we have another mission that is finding the same. This means that we can trust our Planck results. We can trust them because it's reproducible. It has been reproduced. There's also another CMB mission I should mention, the South Pole Telescope, which was in agreement with Planck. So the Atacama Cosmology Telescope was kind of the outlier, and it no longer is. It now agrees with our standard model of cosmology, agrees with the results we found from Planck. So what part of the sky is the new map from? That is an answer that is a very good question. I don't have the answer off the top of my head. You could probably play a kind of spot the difference game. Let's see. Let's put them like that again. Can I move that one up there? Yes, perfect. Which patch of the sky is this? No, we're not going to be able to find this patch of the sky just by looking at it. I cannot remember which patch of the sky it is. I have the impression that it's kind of like down bottom left of the CMB, like the bottom half. But honestly, I cannot remember exactly where it is. There is a map somewhere that puts the two together, but I cannot remember exactly where that map is. Yeah, we could probably use the coordinates that are here, these numbers, to figure it out, but I cannot exactly remember how those coordinates work, like where those numbers go, because I cannot remember my galactic coordinates. There was a map somewhere. I don't believe they have it in this. Do they have it in this paper? This paper, this is one of the results. Also, here's the black and white version, just if you want to see that multi-frequency one. We're scrolling the paper together here to see if I can find the map, because I think there was a map in this paper, but maybe not. Aha, there it is. Okay, so which part of the map is it? It's everything you see in yellow. So the yellow part of this map here is the one that was just mapped by the Atacama Cosmology Telescope data release 6. There we go. See, found a map. I can answer your question. So it's the yellow patch. I believe the one that we were looking at, the patch of the sky that we were specifically looking at, is kind of in the center, just to the bottom, which is about what I said. So that's pretty cool. Okay, let's go back to the questions here. Let me just get rid of the paper next to me. And here you can see I'm not pulling the images from a press release, I'm pulling them from the actual scientific paper. Okay, so what part of the map is the new sky from? Or what part of the sky is the new map from? That was the question, answered that one. How long did it take to collect this data? Is the next step mapping the entire sky? Excellent questions here, Ben. So the next step is not to map the whole universe. This is kind of the legacy for the Atacama Cosmology Telescope. The reason the Atacama Cosmology Telescope can't map the full night sky is because it's tied to the surface of the Earth. So Planck could map the full night sky because it went to space. So then it can do the full sky survey. But because it went to space, you can't give it as intense precision. So the idea here is that these missions are very complementary. Planck is supposed to look at the whole sky and do temperature, and then Atacama Cosmology Telescope stares very intently at a smaller patch of the sky to figure out what is happening in that patch, but it can stare very intently there because it doesn't have to do the whole sky, it can just focus on one region. So then we get more precision. So we can go to smaller scales. So the information that we get from Atacama Cosmology Telescopes expands what we already knew from Planck and now is in agreement with Planck. As to how long did it take to get this data, the maps are based on data collected between 2017 and 2022, so 5 years. It took 5 years staring very intently at one region of the sky to get this map, which is pretty cool. Just have a cat here in my nose. My cats are currently shedding, so there is cat hair literally on every surface of my house, despite the fact that I cleaned it this morning. And I have cat hair on my face as well. Just a very quick overview, because Takino asked about the difference between the blue and the orange here. So in the early universe, we have these photons that are breaking away from the protons and the electrons. As the protons and electrons combine together to form the first atoms, the photons break away. But in this early universe, we had overdense and underdense regions. So regions where you have more protons, more electrons, more photons, and regions where you have fewer of these. In the regions where you have more density, it's going to take a bit longer for the photons to break away because they need to overcome the gravitational force first. While overcoming the gravitational force, they are going to lose a lot of energy. So by the time they reach us today, they have lost more energy because they first had to get away from the overdense region. So the overdense regions in the early universe have less energy in the photons today, so they're the bluer regions, whereas the orange regions correspond to regions in the early universe that were less dense because the photons didn't need to lose as much energy to break away. So the difference here between the orange and red is just the density of the universe at that patch in the early universe. And by taking the statistical properties of these orange and blue regions, these overdense and underdense regions, we can figure out the standard model of cosmology. That's a quick overview there. Okay, question from Paul here. Is it fair to say this tightens the sigma for the CMB conclusions of what the constraint should be, and therefore makes attention even more tense versus other models? It does not tighten the constraints too much on these parameters, but it does give us kind of another independent measurement of these. Of course, you can combine them, but when combining them, there's a risk that you're double counting. So usually you don't combine them because you're measuring the same thing. So combining them, stacking them on top of each other is kind of using the same information twice. So you can do that. You can combine them. But it doesn't really change our results in terms of the Hubble tension or the sigma 8 tension. Comment from John here. Let me just finish my tea because it's cold at this point. Okay, tea is gone. Tea is gone. Let me put the mug down. Tea is gone. There we go. Now, comment from John here. Can precise Atacama Cosmology Telescope data from a small patch of the sky be used to make more precise assumptions about Planck data in other parts of the sky? Sort of. So the cool thing about Atacama is that it's also measuring the polarization. And the polarization should give us the same kind of lambda CDM values. So we can do a cross-check because we can get the temperature from the CMB and the polarization from the CMB from different missions, one from Planck, one from Atacama, and see if they're telling us the same story. And it turns out that, yes, they are telling us the same story. So this is very, very cool. We generally think that the sample, as you can see in this map here, There's not really a special spot. It's pretty much the same. You could take any chunk of the sky, and because we're interested in the statistical properties, you probably get the same whichever chunk of sky you get. So even though Atacama focuses on one part of the sky, we expect that the results there apply to the whole of the CMB. Sorry, one sec. Yeah, so we expect the results to apply for the whole sky. So even though Atacama is focusing on one region, the results are broadly applicable. Okay, question from Joe Business. Anything new in the universe? Yes, this is exactly what we're talking about today. First new thing that I've discussed, results from the Atacama Cosmology Telescope, perfect agreement with Planck results. So the CMB is pretty robust. This is good news, pretty robust. Okay, let's move on because I realize that we are absolutely going to take a while today because I still have 3 missions to discuss and we're already 1 hour in. So we need to speed up slightly, but we need to save space because I am saving my favorite to last, which is Euclid. Okay, so 18th of March, CMB mission says, yes, Planck is good. I like this. As someone who worked on Planck, as someone who has always said Planck, CMB, you all know that this is literally my favorite image in cosmology. And to get an independent experiment saying this is correct is kind of nice. Okay. I talked a lot just now about the sigma, the S8 tension. The S8 tension, where if we ask the question of how much does matter clump on specific scales, we get different answers depending on how we do the measurements, where if we do use a CMB and project it forward, we get one number. And if we use weak lensing or cosmic shear experiments, which are measuring the universe today, we get a slightly different lower value. So CMB says the matter clumps a bit more. Kids said that it clumped a bit less. There's also another experiment known as the dark energy survey, not to be confused with the dark energy spectroscopic instrument. The dark energy survey was kind of in between the Planck, it's another cosmic shear experiment, and it was kind of in between the Planck results and the kids' results. So if you just compared this to CMB to Planck, there was a 2 sigma tension. If you compared kids to Planck, there was a 3 sigma tension. Okay. Kids legacy, the final kids release. Kids is the kilo degree survey. Where is kids based? I do not remember where kids mission is based. Let me just figure out where kids is because now I'm curious. It's an astronomical wide field survey. Yes, where is kids? Not that this is relevant. I just can't remember where in the world kids is. Where do we put kids? Okay, I cannot remember where kids is based. It does not matter. It is not the point of this conversation. Just can't remember where kids is. Okay, irrelevant for the sake of this conversation. Kids is somewhere here on Earth. This is fine. I do not need to know. This is bugging me because I cannot remember what country it is in. Okay, it does not matter. We will figure out where kids is at some point. I did not immediately find this information. It is not the point of this conversation. Anyway, kids, ground-based mission, measuring cosmic shear. And let me just go to something over there. There we go. So kids, ground-based mission, measuring cosmic shear. Oh, I just realized there's a bunch of new comments and I was stuck. So let me just check the comments first before we jump into kids. Comment from Takina, I prefer we had hologram maps to look at because the universe is now flat, is not flat. Indeed. If you could kind of project that map around you, it would be a lot easier. You can actually project these maps around you as Paul is saying. Some people have created these maps where you can just look around and see what is happening. So I don't know how I got stuck and I was wondering why comments has stopped and now I've realized I have a bunch of comments to catch up with. So yes, I'm just going to catch up with the comments and then we get back into kids properly. So there was a comment from Takina about can you create these 3D maps? And as Paul said, yes, you can kind of unwrap the CMB and fly through it. It's very cool. Question from Prath about when follow up to asking where in the sky it was. I meant more like where do I have to look up to see that patch that they did? Like, is it close to some known planet or constellation? You want to look towards the center of the galaxy. And then you want to look slightly up. And then no idea. There actually was an idea at some point to make a smartphone app. in the same way where you have these kind of planetary maps where you can look and see the stars around you, to kind of be able to zoom in and see the CMB behind that. And I thought that was a very, very cool idea. And I don't think it was ever made, because I was in a discussion at some point of kind of a planning phase for this, and we never progressed with it. And I'm not sure if somebody else did, but it would be very cool if you could project the CMB map on the sky around you in the same way that we do with kind of planet maps. So as for where in the sky is it, I have no idea. Question from John: is Atacama Cosmology Telescope looking at gravitational lensing of the CMB light? Not as much. So it is. There is this whole other thing that you can look at how much the CMB photons are lensed on their path towards us. This is something we already got from Planck, and it's something that we got a bit of information from, also from Akatama, but it's Atacama. Yes, I said it right the first time, but it is not the main objective. The main thing it was focusing on was polarization and also the slight temperature. Okay, more questions here. I just got distracted and lost some questions, but more questions here. Comment from Takina: I can't help but think it's hot and cold when I see blue versus red, and I kind of want to say that the blue backdrop is a neighboring dead universe. Yeah, it is. It is kind of the way we think about things, and these colors were actually chosen specifically to be a temperature gauge, to have the colder ones and the hotter ones. But here it really just does represent the less energetic, colder, and the more energetic, warmer ones. So it's not so much about temperature, it's about the energy of the photons. So the blue, colder regions are really just regions where the distribution of matter in the early universe was different to how it is in the orange regions. Comment from Ben: they say consistently drinking hot liquids contributes to esophageal issues, so cold tea is healthier. Indeed. However, no. Tea needs to be hot. Well, my kind of hot, which is mild, but yes. Question from Takina: what is polarization? Okay, great question. This is sometimes the problem with my long streams, that I introduce things early on and then forget that there might be people jumping in midstream. So just a reminder of what polarization is. Polarization is basically the direction in which the photons are vibrating. So if something is emitting light, like a star is emitting a lot of light, those photons will be unpolarized. They vibrate in every possible direction. So you get photons vibrating in that plane, you get photons vibrating like that, like that, like that. But you can have polarized light depending on the way you create the light, where the light vibrates in a specific direction. For an example, a laser is a highly polarized light beam. So it travels it vibrates in a very specific way. So this is something that we can measure and we can use. You can have polarized sunglasses where you can look at different bodies of water, and you can kind of see different things because of the polarization in the glasses. 4-hour stream path. We are not doing a 4-hour stream, mainly because I have not had dinner, and it is 9 p.m. for me, and it's kind of late for dinner. So I'm happy getting dinner at 10, but not later than that. So we have an upper limit, absolute upper limit of 2 hours, because then I'll just be done. I'll have lost my voice by then. Also, follow up from Takina: isn't Planck something super small? Yes. So Planck was a very famous scientist, and we have a lot of things named after him, including the Planck units, which are the tiniest units we can measure. He did a lot of pioneering work in the for quantum physics, and the Planck satellite is named after Planck. So when I'm talking about Planck data here, or Planck today, I'm referring to the mission that took this map, the Planck mission. Yes, when I was searching for the kids, Prath, thank you for the helpful comment that you put the kids in school. Indeed, I agree. Yes. Okay, so I think I've caught up with the comments now. Just had to do a slight pause because my comments froze, and then something about 10 of them appeared in one go. Okay, so kids, the mission, not the actual, humans. Kids, the mission. In 2020, we had the Kids 1000 release, where at sigma 8, the amount of matter that clumps on scales of 8 megaparsec was 3 sigma away from Planck. DES, the dark energy survey, was somewhere about 2 sigma away from Planck. And this is known as the S8 tension. And it has been kind of a persistent issue over the last 5 years in cosmology, because it's something that, again, is the question of, is our CMB data wrong? Is our lambda CDM standard cosmology wrong? What is happening here? And there's been a lot of work trying to solve the sigma 8 tension. I have 3 papers trying to solve the sigma 8 tension. So there's there's a lot of people working on, just blocking a comment here that was spam. There have been a lot of people working on trying to solve the sigma 8 tension. And one of the driving data points for the sigma 8 tension was the KIDS 1000 release, which was 3 sigma away from Planck. This was until KIDS Legacy, release on 25th of March 2025, so 5 days ago, hot off the press. The KIDS Legacy survey redid the analysis, updated more data, updated pipeline, better control of systematics, better self-consistency. They did their data in a fully blind way, so nobody working on the analysis knew the results until the end. And they actually do the thing where they provide like 3 different versions of the data. Each one has been multiplied by a specific number, and then you do the analysis, and at the end you remove these multiplying numbers to get the actual answer. So this means that nobody working on KIDS knew what the result was going to be until the unblinding day. And this is to prevent people from being biased and adding their own interpretation on the data until the analysis is complete. KIDS Legacy is the most robust analysis done by KIDS, is the most robust cosmic shear measurement done to date. And it is, as the name implies, the final release from KIDS, from the Kilo Degree Survey. It is the legacy release. The legacy release means it's final. We've done everything we could. This is our final data. Final data of KIDS finds an S8 value 0.7 sigma in agreement with Planck. So 0.7 sigma away from Planck, which basically means perfect agreement. It's less than 1 sigma apart. It is completely compatible. Which basically means the sigma 8 tension, the S8 tension, it's gone. It's gone. We still, of course, need data from the dark energy survey, which was also somewhere in between. But people in the cosmic shear community are kind of leaning more towards the fact that the sigma 8 tension was due to an uncontrolled systematic or something that wasn't going the way it should have gone in the cosmic shear analysis. This has been resolved. So 5 days ago, we got the result from KIDS, where the main takeaway is the sigma 8 tension, the S8 tension, which has plagued physicists and cosmologists for 5 years, is solved. Again, if you're the type of person who has spent years working on solutions to the S8 problem, you might not like this result. If you are the type of person who thinks that this was the answer, that the CMB is correct, that, you know, we measured how much matter clumps, we have our standard model of cosmology, you'll be happy with this result. So within a week, we got results from Atacama Cosmology Telescope saying, actually, we agree with the Planck CMB measurements. The Planck CMB measurements are robust. And then we got KIDS Legacy saying the discrepancy we had found with the way matter clusters is solved. We also agree with the standard model of cosmology. So if you're a standard model of cosmology fan, if you like lambda CDM, this is good news. This has been a fun week. I did not know the KIDS results were coming. So I opened the morning paper, saw the press release, saw that, and was like, whoa. And I've since watched talks by the people involved in KIDS, and they're like, yeah, this is our final say on the matter. And our final say on the matter is the sigma 8 tension is perhaps not worth us talking about anymore. You know, I have 3 papers trying to solve this tension, which was fun. But yeah, if you've spent 5 years trying to work on this tension and now it's no longer there, this is an interesting day. Comment here from Worst Karma, didn't they resolve this with a mask on the CMB, basically throwing away data? Yeah, that is one way of doing it, but why would you throw away data? So there's always the question of how you clean up the CMB, and yeah, how much you clean up the CMB and how much you mask the data. So that is something to take into account. And of course, you can use different parts of the CMB data, and you got a slightly different value of the value of S8. But if you use the full CMB data and the full kids data, you were getting slightly different results. But not anymore. Now they do kind of agree with each other. So there's a question here from Prath of how much is 1 sigma difference in terms of percentage? How much is 1 sigma difference in terms of percentage? Let me think. So we generally say that yes. So when we say that things are less than 1 sigma apart, I can't give you a percentage off the top of my head. I mean, we have kind of our confidence in the measurements. So if it's one sigma, we can say that like we're very, very, very sure that most of these measurements fall within the same contour. But I don't have the exact percentages. Let me just see if I can calculate this. Yes, I can't remember the numbers off the top of my head for the sigma, but yes, you can convert that. Thank you for joining, Takina. You have to go to bed, so I guess you're further ahead than me, further to the east than me. Have a good night. Thank you for joining. You can always watch the replay. We'll go on for another 20-30 minutes. Watch the replay. Thank you for the questions. So yeah, this was a fun week. 18th of March, we get Atacama saying, hey, guess what? We agree with Planck. 25th of March, we get kids saying, hey, guess what? We also agree with Planck and with the standard model of cosmology. Kind of cool, right? So, is sheer data from Euclid not yet released? It is not. There will be a mission that has more to say on cosmic shear, and that is Euclid. And I will get to Euclid at the end today. But it looks like our standard model of cosmology is doing pretty well after everything that's happened. Until DESI. DESI, Dark Energy Spectroscopic Instrument. Some of you know that I'm a huge, huge, huge fan of DESI. I just realized I forgot to load up an image that I wanted to load, so let me just load it one sec. DESI 2025. Let's see if I can find this. I'm just looking for the new map that we got from DESI. Yes, here it is. Here's the new map. This is the image I wanted. Let me get rid of the ads. I don't know what page I opened it on, but there are ads. Okay, so DESI, Dark Energy Spectroscopic Instrument, ground-based mission that started in 2021. It is taking the most detailed map of the late universe ever. It is mapping all of the galaxies, all of the galaxies in the night sky. Last year, we got the first release from DESI. Yeah, as Paul was saying, about 68% of the data falls within 1 sigma, pretending everything is smooth and normal. So when you're comparing two measurements and you say they're within 1 sigma, what you're saying is that most of the data falls within 68% of most of the other data, if that makes sense. But I don't think those are the exact percentages that help in visualizing like how far away things are, which is why I wasn't giving an exact answer to that. But yes, that's one way of explaining it, but I'm not sure if that clarifies things. It does clarify things. Thank you for adding the 68% there, Paul. But yes, it does mean when we say things are within 1 sigma, we're saying 68% of the data of each mission is in agreement, at least. Okay, so Dark Energy Spectroscopic Instrument, taking the most detailed map of the late universe ever. Last year, on the 7th of April last year, we got this map. This was the best map we had at the time of the universe. This was about 6 million galaxies mapped. This contained 1 year of data from the Dark Energy Spectroscopic Instrument, but they now have released year 3. So even though they only released year 1 a year ago, now they're releasing year 3. The reason for this is they take the data and then they spend quite a while analyzing the data. So it took quite a while to analyze the first year of data because they had to develop the pipelines. But then by the time they've released year 1, they already have enough data for years 2 and 3 as well. And now they have all the pipelines, so now it's quicker. So April last year, we got DESI year 1. We got this amazing map here. Last week, or 2 weeks ago by now, on the 18th of March, we got year 3 data. So we got a new map. And this is the new map. Let me put them side by side so we can have the comparison. Can I switch to this view? I'm just going to turn myself off momentarily here. Back on a minute. There we go. That's the view I want. If you compare the one on the left here, let me just zoom in a bit, this one here, to the new one here, we have so much more data. This is so cool. So this is, let me switch them around. That's a much better view. This is the new slice of DESI data, the new map that we have, the most detailed 3D map of the universe today that we've ever had. Several million galaxies. So last year, with the first one, we had 6 million galaxies. Now with the one that you can see here, the new DESI results, we have 18.7 million galaxies mapped. 3 times the amount of data we had before. This is so cool. This is amazing. Every dot here, just so we know what we're looking at, every dot in these images represents a galaxy. There's kind of this triangle shape in both directions because our galaxy lies at the center, so we can't see to either side because of the galaxy. So we can look up and we can look down, and you get this kind of triangles in each direction. Every dot here represents a galaxy. Every dot here is a galaxy out there in the universe that we have been able to measure with the dark energy spectroscopic instrument. Last year, I did a whole stream about this data. I could do a whole stream about that data there as well, but I want to talk about so many things today that I'm just flashing the image, but I will do due diligence and get a full stream on this data because it is so cool. Okay, Paul and Press, thank you for clarifying the discussion that I skimmed over here. I agree with everything you said here in the comments. Okay, so DESI 1 year, DESI 3 years. This is amazing. Just the precision on this map here, it is so beautiful. It is such an amazing map. But DESI is not just taking pretty pictures. It is taking pretty pictures, but that's not the only thing DESI is doing. DESI is measuring dark energy and how dark energy has changed throughout cosmic evolution. By looking at all of these galaxies, we can get an idea of what the matter in the universe is doing today and what the matter in the universe was doing in the past. So we can really use this to map out how matter has changed and therefore how dark energy has changed over the last 10 billion years of cosmic evolution. So I started earlier on today by saying that in our standard model of cosmology, dark energy is a constant. It is a cosmological constant. It's behaved the same throughout the history of the universe. It's a big thing. It's an energy that is driving the accelerated expansion of the universe. That is everything we know about dark energy. Last year, when we got the first DESI results, the DESI results were pointing towards dark energy changing over cosmic time. Dark energy kind of thawing, so changing in intensity, kind of slowing down in a way, which means it would not be a cosmological constant. At the time when this was released, back in April last year, this was cool. This was very, very cool. First year of DESI data is showing a preference for evolving dark energy. But that was only 1 year of data. Now they have 3 years of data. And sometimes, as we've seen today with kids and with Atacama Cosmology Telescope, sometimes when you get more data, anomalies go away. That is not the case for DESI. They now have 3 years of data, and they find an even stronger preference for time evolving dark energy, for dark energy that is changing over time. When just using DESI and CMB data, they are 3 sigma away from the standard model value. When they also include supernova data, depending on which set of supernova data they use, they get a preference of up to 4.2 sigma away from standard cosmology. So let me just show you, I'm going to show you a graph here. I'm going to look at the actual scientific result here. Can I zoom in on this one? I believe I should be able to zoom in on this one. Yes, there we go. That did not help much. Okay, so what we're seeing here is W0, WA. These are just telling you on the horizontal axis, so left to right, this is how dark energy behaves today. And top to bottom, vertical axis, this is how dark energy has changed throughout history. We expect that dark energy today has a W0, the equation of state, of -1. And according to lambda CDM cosmology, WA should be 0. So we expect our standard model of cosmology to be here. This is what standard model of cosmology wants. This spot up here where the crosshairs are. What DISY, CMB, and Supernova Dark Energy Survey Year 5 is showing us is over here. What this green contour is showing you is the 2 sigma preference. So it's saying 68% of the data is in the first one, the dark one, 95% of the data, or 95% chance that the data is in this circle. So there's a 95% chance that the data is over here. It is not up here. So this is a 4.2 sigma difference. 4.2 sigma difference between what lambda CDM wants, which is the crosshairs, and what the dark energy survey is finding, which is over here. So what this is telling us is that I keep moving things on my screen. The fact that I have both the slides that I'm showing and the screen that I'm sharing, and I have my notes open, there are so many things on my screen, and I keep getting confused and pressing the wrong buttons. Okay, so the preliminary results from DISY, question from Ben here, do the preliminary results from DISY mean we may be in a multi-universe and the universe may exist inside a black hole? That is, I have not seen that interpretation of the DISY results. The DISY results are still quite fresh, but I have not yet seen anyone connecting it to black holes. What this is basically telling us is about the behavior of dark energy, about how dark energy is behaving through cosmic evolution. And let me just go, if I can, right to the top of the questions, because right when I started this stream, there was a question from John. I saw a really interesting study that used DISY data to find hundreds of new intermediate mass black holes. Did you happen to see that one? I did not, no. But that's something I will also look out for. So this is not leaning towards modified gravity, just to clarify here. This is leaning towards a new understanding of dark energy. And this is a very cool thing. When DISY Year 1 data was released last year, this was kind of cool, but it's Year 1 data, it might go away. Now they've got Year 3 data, 3 times as much data. They've gone from 6 million galaxies to 18.7 million galaxies. This result is here to stay. This is very, very cool. They've mapped 18.7 million galaxies, going back 10.5 million years of cosmic evolution. Sorry, 10.5 billion years of cosmic evolution. And the conclusion that they found is dark energy might be changing with time. And that is very, very, very cool. Now, it also doesn't mean that the numbers that I gave at the beginning are wrong. It doesn't necessarily mean that the numbers are wrong. I'm just going to go back to the numbers to show you which ones I mean. Let me just go back to the start of my slide deck here. I started this stream by talking about the standard model of cosmology. And let me just wait for that to stabilize. Yes. I started the stream with this. We have 4.9% normal matter, 26.2% dark matter, 68.9% dark energy. This is still true. What I also said is dark energy is driving the accelerated expansion, and that is everything we know about dark energy. This might no longer be true. Dark energy is a cosmological constant, it's lambda. This might no longer be true. What DISY is telling us is that this dark energy is changing throughout cosmic evolution. So we know something about dark energy that we didn't know before. It is still at 4.2 sigma. It is not enough to claim a discovery. It is not enough to say, let's throw out everything we knew about cosmology and start again. But it is enough to ask the question of, where's this coming from? So within a few days of each other, Atacama Cosmology Telescope found agreement with Planck. Planck is good. CMB is good. Standard model of cosmology is robust. Kids, on 25th of March, sigma 8 tension is gone. We agree with Planck. We agree with standard model of cosmology. It's robust. DISY, 18th of March. Let's talk about that. So DISY doesn't mean we need to throw out a standard model of cosmology, but DISY might actually be shedding light on the nature of dark energy. So I might no longer have to, those of you who watch my stream often know that there are some things that I do almost on autopilot now. And when I show this pie chart and I do the whole spiel here, It's basically always saying the same thing. And I get to dark energy and I say, dark energy is driving the accelerated expansion of the universe, and that's pretty much everything we know about dark energy. This might no longer be true. It also means that the lambda in lambda CDM might not be a cosmological constant. So I also said at the beginning, our standard model of cosmology has CDM for cold dark matter and lambda for cosmological constant. It might not actually be a constant. So this doesn't mean we need to throw it out, but it does mean there's something very interesting happening here. So in the same week that the sigma 8 tension kind of disappeared and the tension between cosmology datasets disappeared, the tension between dark energy, spectroscopic instrument, and CMB reappeared, became stronger. You win some, you lose some, steps forward, steps back. It's very, very, very cool. Did Dizzy tell us which way dark energy has been changing, increasing, or decreasing? So I heard it phrased as dark energy is thawing. So if dark energy is thawing, it is getting colder, so it is decreasing. So it is gradually kind of changing. It is decreasing slightly, I believe. Question from John here. If dark energy changes over time, then have cosmic redshift measurements all been miscalibrated? Probably not, because when we're talking about cosmic redshift measurements, these are very, very close. They're very small, very short distances. And when we're talking about how dark energy has changed over time, you need to really look at multiple epochs of cosmic evolution, several billion years, to get the full idea of dark energy changing. It's not something that changes one day to the next. So it's not something we're going to notice in our local universe. But it is something that we absolutely need to pay attention to. So there is a very nice blog by Peter Coles called Telescoper, which is an acronym for Peter Coles. It's a very nice blog, and he presents new results. And he has a summary of the Atacama results, of the kids' results, of the Dizzy results. And he concludes the Dizzy results with this quote, which I think is really nice. There is the quote from Peter Coles here. We're seeing an evolutionary change from we have no idea what the dark energy is, but we think it might be a cosmological constant, to we still have no idea what the dark energy is, but we think it might not be a cosmological constant. So that is the main result from Dizzy. We get this gorgeous, gorgeous map, this beautiful map that they've released. Let me bring it up again. We get this amazing map from Dizzy, most precise map of the 3D universe ever. Very, very, very cool map here. And also we get the result that dark energy might be changing throughout cosmic evolution. So that is very cool. What a week, huh? Where we get cosmology results from Atacama, we get kids, we get Dizzy, all within 7 days of each other. And most of these were not announced in advance. We didn't know they were coming. There were leaks, there were rumors, but suddenly waking up to this and being like, whoa, what a week. What a week. Okay, question here from Karma. Didn't Planck 18 also have a slight preference for a closed universe, still waiting on someone taking that quadrupole anomaly of the CMB seriously? It did indeed. And Atacama Cosmology Telescope did not find any evidence for anything moving away from a flat universe. But there are still some small anomalies that need resolving as well. There are still some things. But yeah, this is all very cool. So sigma 8 tension might have disappeared, or S8 tension might have disappeared. Atacama Cosmology Telescope and Planck are back in good agreement, but Dizzy does not think the story ends here. Been a roller coaster for a couple of weeks for cosmology, and we are not done. We are not done, because I've saved the best to last, or the best, I've saved my personal favorite to last. But now we're going to move a bit away from like pure cosmology, because we have to talk about Euclid. We have to talk about Euclid. Euclid, as many of you know, is my second favorite space mission. My favorite ongoing space mission. Obviously, I love Planck, as you all know, and Lisa has a special place in my heart because that's the one I work on. But Euclid is a mission by the European Space Agency that is aiming to map the dark matter and dark energy in the universe. It is the dark detective, as they like calling it. Euclid launched in 2023, and it was an amazing launch day. It's at L2 at Lagrange point 2, and it's taking data and it's trying to map how galaxies behave. It is a very, very cool mission. And some of the things we've got from Euclid already have been the small kind of releases, proof of principle that it knows what it's doing. I did a stream about it last year because last year we got the Euclid and DAISY results within 3 weeks of each other. This year we got the Euclid results and DAISY results within a day of each other. So for anyone keeping track of the timeline, Atacama Cosmology Telescope, 18th of March. Kids, 25th of March. DAISY, 19th of March, 18th of March, and Euclid, 19th of March. So on the 19th of March this year, a year and 18 months after the launch, we got Q1 from Euclid. So Q1 is the quick data release 1. Quick data release 1 is the first batch of cosmological data, the first batch of data with the precision, the final precision that Euclid is going to have. We've had some kind of pretty images released already. We've had some astrophysics results already, some small ones. But the quick release is kind of the first proof of principle of, or first showcase of the depth and the precision that we can expect from Euclid. Want to be very clear here that Q1 from Euclid does not include cosmology results. So Euclid has not yet told us anything about dark matter or dark energy. Instead, from Euclid Q1, we get detailed maps or detailed pictures of the universe showing us the type of precision that we can expect to achieve with Euclid. There were 27 scientific papers released with Q1 and a bunch of cool images. So just to be clear here, Euclid has not yet released its cosmology results. We expect those early-ish next year. But Euclid has released its quick release 1, where it's got the images with the precision that we expect them to have at the end. So QR1 is 1 week of data. Euclid is going to take data for about 4 years. That is bothering me. Let me just fix that. There we go, much better. Euclid is going to take data for about 4 years. In QR1, quick release 1, which was released on the 19th of March, there is just 1 week of data, just 1 week of data. In 1 week of data, Euclid spotted 26 million galaxies. 1 week of data, 26 million galaxies. Imagine what it's going to do with 4 years of runtime. And just to get us started, Euclid has looked at a 63 square degree patch of the sky, 63 square degrees. Once it's done, Euclid will have mapped 14,000 square degrees of the sky. So this is a very, very, very small fraction of what Euclid is going to do. And this is just showing us the precision that Euclid is going to achieve. Okay, let me just reply to the comment from Lethargo, and then we get into the Euclid, the images. Comment from Lethargo here. An impressive amount of effort going into all of these cosmology surveys. Indeed. Yeah, I cannot overstate enough how much of an international collaboration this is. Like all of these cosmology experiments, there are hundreds of people working on them. And it's such a huge amount of effort to get these data releases, to get this information out, to cross-check, to make sure everything is fine. All of these analyses require so much effort and so much work. And it's amazing that there are people working on this and getting us these results. It is a huge effort. And often science is slow. Things progress quite slowly. So to have a month or a week even where we had 4 major releases, or 3 cosmology releases and Euclid first QR1, this was amazing. And I didn't know a lot of these were coming. I knew Euclid was coming. They did a big countdown on social media. I suspected that DAISY was coming soon, but the others were surprising to me. And I work on these topics. So to get 4 major releases, you know, I keep mentioning the previous Atacama Cosmology one was in 2021. Kids was in 2020. DAISY was a whole year ago. To get 4 of them in the span of 7 days, that was just amazing. I was also having an insanely busy week for other things. So then catching up with all of this was really, really cool. But let's get into Euclid. So Euclid for now has just taken data for 1 week of 63 square degrees of the sky. Eventually, Euclid will spend 4 years mapping 14,000 square degrees of the sky in as much detail and as much quality as the images I'm about to show you. So there are 3 regions of the sky that Euclid focused on, 3 regions that Euclid zoomed in on. So I'm just going to show you a map, and this map is not Euclid's map. This is a composite image using data from Planck and Gaia. So this here is just showing you the patch of the night sky that, what happens if I make that bigger? Does that make that bigger? It does make that bigger. Okay. So what you can see here is a composite map made using data from Gaia and data from Planck. And the 3 yellow splodges that you see are the different regions that Euclid has zoomed in on. So we have the north one, top left. Yeah, we have the north one up here. We have the south one here. And we have Fornax down here. So north, south, and Fornax. And these are the current regions that Euclid has looked at. So we are going to go from my least favorite to my most favorite, because we have to do it like this. So first of all, we start with the south one. This is the south, the south map that we have here, Euclid Deep Field South. And I'm not sure how well it's coming through on the phone, but this is an incredible amount of data that we have here. This is just an insane amount of data. And let me show you what I mean by this. I'm just going to change. Let me actually just open up my other screen now that I don't have a cat sat on my screen, because then I can maybe distribute things in a way that is easier for me to navigate. One sec, let me put that over there. Whoops, not what I intended to do here. Also not what I intended to do here. Okay, we were on south, Euclid South. Okay, so just want to show you here that we can zoom in, and we can zoom in, and we can keep zooming in on these deep field maps. And we can keep zooming in. Again, every dot here is a galaxy. Zoom in again. This is as far as we go. Look at this amazing precision. So this is the deep field south. And this is just amazing. So the ones that have more distortion, kind of like this one here, this is a star. And the others here are mostly galaxies. You know, I grew up in an age where the Hubble Space Telescope Deep Field was the most impressive deep field we could have. That has been superseded by JWST. And now look at this. This is, you could just scroll for hours here and look at all the different things you can find. Just let me go back just to show you how far in we zoomed here. So this is the Deep Field South. This is one of 3 that Euclid treated us to this week. So this is Deep Field South. Then we also have Deep Field North. Deep Field North, again, the amount of precision that we have here. I believe I wanted to leave Deep Field North to last, but anyway. Deep Field North. Also, the amount of precision that we have here. Again, we can zoom in and just keep zooming in. And it can still go more. And you can see here all the galaxies. You can find nebulas. You can find the Cat Eye Nebula if you look close enough. Let me zoom out again just to show you how far we zoomed in. I hope this is showing up well on your screens. If not, go to the web pages and look at them. You can see the web pages on my browser here. You can also just search for ESA Euclid images, and you'll find them. And then we have Fornax. Fornax is also one that you can just zoom in and keep zooming in. I know I'm just showing you a bunch of stars here, but the precision that we have here, this is incredible. This is amazing precision. Look, there's a pretty galaxy here. Can I zoom in again on this pretty galaxy? Yes, of course. There we go. Just the precision that we have here is amazing. These maps are absolutely amazing. And again, this is Euclid with 1 week of data. Euclid is going to operate, let me get rid of this. Yeah. Euclid is going to operate for 4 years. This is just 1 year of data, 1 week of data. And the amount of precision that Euclid got here is amazing. The fact that Euclid has been able to already do this after 1 week of data is so cool. So again, Euclid was looking here at a 63 square degree parts of the sky when you add these 3 maps together, 63 square degrees. It is going to cover 14,000 square degrees. So the map I showed you before, you saw there were just these like yellow splodges, yellow regions that were tiny. By the time Euclid is done, it will have mapped about 1/3 of the entire night sky, which is amazing. So this is not just pretty images. There were 27 papers accompanying this. And also, I'm not showing it here, but Euclid has then zoomed in on specific galaxies. You can get a mosaic of all of the galaxies or some of the main galaxies that Euclid has imaged. Oh, it's so cool. It's so cool. You can spend hours browsing these photos. I specifically wanted these on the webpage so that I could zoom in and show you just how much you can zoom in here. So there is the very nice question here as to why Phoenix is my favorite. And the reason it's my favorite is just because it's pretty. I know I like all three of them. I really like all three of them. I like Phoenix. Let me just open it up again because you can very easily find this one here. You can also find similar pretty things up here. It is just so cool. So yeah, Euclid is a space telescope. It is in L2, Lagrange point 2, hanging out with JWST. It's also the same place where the Planck mission was. It's amazing. And this is a teaser of what Euclid is going to do. This is just, look what we can do in 1 week. Here's 27 million galaxies. Just imagine what they're going to do with 4 years of data. It is so cool. So Euclid did not yet give us any cosmology results. But Euclid did give us these amazing maps and 27 scientific papers to go with it. I highly recommend just finding these images online. Go to the European Space Agency webpage, search for Euclid images. You can spend hours staring at these, picking out your favorite galaxies. I have. It is so cool. So I had to mention Euclid because even though, they haven't broken our standard model of cosmology, they haven't given us any cosmology results yet, they have just given us these amazing deep field maps. My stream appears to have frozen. Let's see if that comes back. Oh no, where did my stream go? There we go. It's back now. So question here from Pratt, what happens to those telescopes once their mission is over? They are decommissioned, which means they they're put into a place where they won't bother the other telescopes that want to go hang out in L2. They're moved off of the main trajectory, but they just kind of hang out there. They're switched off. They're decommissioned, they're switched off, and they just go there to die. So it's also the thing that, Euclid is at L2. Planck's skeleton is there. JWST is at L2 as well. There's like a bunch of old turned off telescopes there as well. Now I'm just remembering why we don't go past the 90 minutes usually, because my voice is gone. Talking for an hour and 42 minutes at this quite active pace and enthusiastic pace, my voice is gone. Yes, as John is pointing out here, it is absolutely worth downloading the full resolution Euclid images and just zooming in and zooming in and zooming in and zooming in some more, because you can zoom in as much as you want. Okay, so it's been an eventful few weeks for cosmology. 18th of May, we got the Atacama Cosmology Telescope telling us, recap of everything I said in the last hour and 43 minutes. 18th of May, we got the Atacama Cosmology Telescope telling us that in its data release 6, the tension that it had found, the inconsistency that had been found before between the different CMB missions, between ACT and Planck, the 2.5 sigma tension that was in DR4 has disappeared in DR6. 18th of March, we also got results from DESI, Dark Energy Spectroscopic Instrument, telling us that dark energy might be changing throughout the history of the universe, and this is not compatible with our standard model of cosmology. 19th of March, we got Q1 from Euclid, where Euclid kind of proved the amount of precision, just showed off the amount of precision that we're going to have, and released these amazing deep field images. 25th of March, I think I just said May, March, all of these are March, obviously. 25th of March, KIDS releases the final KIDS Legacy, where the previous sigma 8 tension, the tension in how much matter clumps at specific scales that had been present between KIDS and Planck, has gone. So if you're if you're a Lambda CDM person, it's been an eventful week. It has been an eventful few days. And when all of these results came out, I thought of doing a stream last weekend, but I was hosting a party at my place. I saved it all up for today. Sometimes, God, my voice is gone. Sometimes you'll come on and you're like, what is new in cosmology? I'm like, well, not much. But today, it's like, what is new in cosmology? Like, well, I'm going to need an hour and 45 minutes to answer that question because I am laughing because what I have a cat tower the other side of the screen, like at the back of the room, and one of my cats is just sat there staring into the wall. Like there are no thoughts going through his head. Good day. No, there are no thoughts going through that cat's mind. He's just staring blankly into the wall. Okay. Wrap up some questions here. But yes, as I was saying, sometimes I come in here and I'm like, well, there's nothing new in cosmology. Let's talk about some old stuff. And this time I'm like, well, what's new in cosmology? A lot, actually. A lot of very, very cool things have happened. Let me know what your favorite is of what I've talked about today. Are you happy that cosmology is now in agreement with Akatama and Planck? Are you happy that the sigma-8 tension has gone? Are you sad that it's gone? Do you think dark energy is changing throughout time? What do you think of the Dizzy results? Which is your favorite Euclid map? Do let me know. Leave comments. Let me know your thoughts. You're welcome to. If anyone just sends me a message like my favorite Euclid map is this, I will absolutely reply to that because that is a cool thing to say. Comment from Ben. Just noticed your cosmology t-shirt looks great. Thanks. I love this shirt. Got to show you the shirt in full glory. This shirt was thrifted. This jumper was thrifted. I paid €8 for it. A friend of mine actually saw it in a secondhand shop and took a photo and sent it to me saying, who would wear this? I was like, me. I would wear this. Please get it. So that is how I got this. So yes, when the missions get turned off, they do just become space junk, unfortunately. Especially the ones that are at L2. There's no energy that we can use. We don't have energy to bring them back. So they just become space junk. Comment from Lethargo here. I hope they can get an extra year or two out of Euclid somehow so they can point it at other stuff or revisit and deepen some fields. Yeah, that sometimes happens. Sometimes missions go on longer than planned, and it is really, really cool when that happens. Okay, but yeah, they basically push the mission somewhere so it won't be in the way, it won't be bothering other things. He is now staring blankly at me. I think he's realized that it's dinner time. Okay, can dark energy affect your voice like helium? No, but talking for an hour and 50 minutes can absolutely affect your voice. Dizzy is definitely your favorite result, Ben. That is an excellent choice to go through for. In terms of pure scientific value, Dizzy is my favorite as well. In terms of just personal excitement, the new CMB map from the Atacama Cosmology Telescope has to take it. But also the Euclid images, yeah. Mito, you enjoyed the Euclid deep field images? Yeah, that is a fair choice. That is some absolutely valid choice. I'm excited by all four of these results, as you can tell. I know I was quite hyper today, quite up, but all of this is exciting, right? It's exciting. Almost a 2-hour long stream. This has got to be a record. This is definitely the record on YouTube, I believe. I hope by next stream you have some follow-up from my solo quarks from virtual particle generation. So, about that. I'm not answering your question, Prath, by any means, but next week I will not be doing a stream. There will be no Cup of Cosmology on April 6th. And the reason for that is because I'm at a concert. And I'm really excited about this concert, so there will not be a Cup of Cosmology next week, which means Cup of Cosmology will be back on the 13th of April, same time as always. That is 8 p.m. if you're in Finland, 7 p.m. if you're in mainland Europe, 1 p.m. on the east coast of the US, 10 a.m. on the west coast of the US. There is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone. Do check that out. You can also always find my email address, contact@cupofcosmology.com, where you can get in touch if you want to ask me any questions or if you want to tell me what your favorite part of today's stream was. You can also find me on Mastodon, dchooper91_Cosmo at astrodon.social. Okay, also, is the Event Horizon Telescope working on any new black hole images? Not to my knowledge, but yes. Okay, this has been super, super, super fun, everyone. Thank you for joining. We've had a lot of really cool questions. I got to talk about 4 very cool things, in my opinion. This has been super fun. Almost 2 hours today. You can't complain. Who is performing at the concert I'm going to? So it's a mix. It's a rock orchestra. So it's a big orchestra performing covers of rock songs. And I love rock songs played on classical instruments. So yeah, I'm super excited. It's like a 2-hour long concert. And it's covering, I know it features some of my favorite rock songs. It's going to be good fun. Your favorite today, Paul, is the thought of a whole new concept of what dark energy and cosmological constant could be. Yeah, it's exciting. It is a good time to be a cosmologist. It has been an exciting week. I've had an exciting week personally for other reasons as well. But overall, it's been an amazing week for cosmology, an amazing last 10 days for cosmology. This has been great fun. I'm very glad to have had you all here. Thank you for the questions, for the comments, for the interaction. It's always really, really fun. Whew, I am tired. It is dinner time. Thank you everyone for joining. This has been great fun. Cup of Cosmology should be back in 2 weeks, same time as always. I hope to see you all there. And I hope in the meantime, you all take care of each other and stay curious.